what I want to talk about today is that when we use constraint solving, our solvers produce solutions. And these solutions have an impact on the people and the resources that we're optimizing over. And so how can we actually empower planners and end users to use our technology for the good, according to their own principles? That's a bit the idea. So it's about explanation techniques. The presentation is actually a runnable notebook, so all code and examples I will show will be run live. The slides are on Casein. You can use HTML exports, for example, and they will also be on our repository because this is an extended version of a tutorial that we gave at the CP last year. Right, so clearly, you know, constraint solving used to solve lots of problems, vehicle routing, planning. So these are team allocation problems and so forth. And so our current paradigm is that of model plus solve, where you declaratively specify your problem, and then you use a solver. Maybe you add a global constraint to it, but you still use the solver as is after that. But what if the solver doesn't find any solution? Yeah. Or what if the user does not like the solution because of the impact that it has on the people or the resources that it uses? Or what if the user expected a different solution, a solution in which certain properties or certain elements are present and the others are not, right? So what do we do in that case? And that all of these questions go beyond the simple model plus solve. And just pressing the button once cannot answer these questions. And that's what we'll talk about today. But first, a bit about the bigger picture. So the model plus solve paradigm assumes that there's a planner or an end user and that they give their input into a system and into the model and to the solver. And so in our lab, one thing that we're doing is we're using machine learning to make that a bit smarter. For example, to predict energy prices based on historical data, and then do those predictions taking into account what their effect on the optimization is. So what the error after decision making is. We're also using it to learn preferences based on historic solutions and so forth. So I think that's one way to make our systems more adaptive to the environment, to the human context in which they operate. It's not the content of the talk today. The second way is that this is a very one-way direction, and we just observe what the data is, what the input is, and we input models. But the talk today will be about how can we actually make this a two-way communication, where a solver can also be asked to explain why it made certain decisions, or ask what alternative options are that do satisfy certain other properties. And then I think the end goal, as we have in our lab a large European project about this, I believe that what would be very nice if we could work towards is to have this be a conversational and a stateful interaction. So not just a one-time thing, but where there is a continuous learning interaction between the user and the problem that they are trying to solve. And so most lately, we're also using large language model technology, so you can talk to Kostis and Thomas from the lab if you want to know more, if you want to see an exciting demo that we're working on. But today will be about explanations, the explanation part. And in general, explainable constraint solving, as we call it, it's about the question, why something? And that something is either a solution or the fact that the solver did not find a solution. So the interaction diagram is the following. So the user specifies a model, which includes data, goes to the solver, and then the solver gives an answer. And so either unsatisfiability or a certain solution. And then the next interaction is that the user asks, okay, so explain why is it unset, or explain this to me. And then we want our system to be able to provide an explanation. So there's another computational task here that we need to perform to be able to answer that question. And so what are the kind of techniques that we can use here? That is what I will review in this talk. All right, so in general, to ask these why-X questions in explainable constraint programming, there's actually two big families of types of explanations. The first type of explanation is a deductive explanation. So when the user asks, why is the solution unsatisfiable, for example, the kind of answer that you produce in a deductive explanation is the thing that causes that unsatisfiability, right? So you want a deductive explanation, a deductive reason of why the initial input caused that specific output. Okay. And then the second big family of explanations are counterfactual explanations. So in counterfactual explanations, it's not about the deduction, but there is some the user is assumed to have an understanding of what they want instead of what they got. So for example, what do I need to do to make my problem satisfiable instead of unsatisfiable? And so it's a very different type of question because they ask for something that is not the case, and it has to be satisfiable, or they ask for elements that need to be present that are currently not present. Okay, and also the algorithms that we'll use are different. Okay. A little side note here is that the word explanation in constraint programming is also used often in a different context, in that of lazy clause generation solvers. So these are solvers in which a single propagator explains to a set solver why it deduced a single domain reduction. And so that's a very specific, and these explanations are always clauses. And so that's a very specific form of explanation that we will not consider here. For us, it's about user-oriented explanation. So we want to provide an explanation at the level of the model, at the level of the information that is present in the model. Okay, so let's start with a toy example just to show this a bit. And so it's a graph coloring problem. In graph coloring, you need to color each node so that two nodes that are connected by an edge do not share the same color. And so you might think, okay, this is a toy example, but there's actually at least one industrial case where a company contacted us and it turned out to be a graph coloring problem. This was a company that manages multiple hotels and they get booking requests from a client. I want to stay 2 days in that hotel. I want to stay 5 days. I want to stay this. And so each of the nodes is one booking request and your hotel has a limited number of rooms, let's say 40 rooms. And you want to use as few as possible because then you have to clean as few as possible. But of course, each of the requests, you cannot put 2 requests in the same room at the same time, right? And that's where the edges come from. So although it's graph coloring, actually there's many applications that can be reduced to a graph coloring problem. So this is our Tor graph. Let's color it. Yeah, so what you do is, well, it's a trivial model. I don't even show it. And so for every edge, there's a not equals constraint, and then you solve it. So you call solve, it finds a solution in 0.003 seconds with a CP solver, great, and it finds a solution with 4 colors. Okay. Now, an end user, for example, that hotel owner might ask, okay, but why? Why do I need 4 rooms? Can't I just put them in 3 rooms? I mean, that would be better, than my cleaning crew has less work to do. Okay, so why 4? Do I trust you? Should I trust you? Okay. So let's, first of all, a deductive explanation of why we need 4 colors would be a cause. So a set of constraints that cause these 4 colors to absolutely be needed. Okay. And so let's say that we make a graph coloring formulation where you can use at most 4 colors, and then solve will be false. And then I will explain later how it works. But then we can compute, for example, the following. Okay, so why do we need 4 colors? What does this tell you? Each of the red edges are constraints that are involved. So you only need to look at the red edges, and then you see that there's actually a clique between those 4 points. And so each of these points is connected to all of the other points. And a clique of size 4 cannot be colored with, it needs to be colored with at least 4 colors, right? That's a basic fact. So this is an example of a deductive explanation of why you can't do it with 3 colors, because there is a clique of size 4 that can only be colored with 4 colors. Okay, so let's continue with the counterfactual explanation. So in this case, the counterfactual explanation would pinpoint to the constraints that need to be changed to allow what you want. And so if the hotel owner says, I only want to use 3 colors, I only want to use 3 rooms. Okay, so what actually in your data has to change so that you can do it with 3 colors? Okay. And then this is the kind of techniques, the kind of answer that techniques we'll look at will provide us. So it will tell us that if you could somehow remove this, this connection between those two nodes, then there actually exists a tree coloring. Okay, and actually we can look at that solution. All right, so if you remove this edge, then indeed we can compute a count, so that would be a counterfactual problem, because the original problem did contain it, but we're removing it. What we get is a counterfactual solution, a solution that was not originally a solution, but because we modified the problem, now we see that indeed we can have a tree coloring. Those two are temporarily apart and they share the same room, and those two now as well. Okay. Good. Now you might think, okay, explanation techniques, you're showing me graphs, maybe this is all toy. Actually, no. So in our lab, we have the Sudoku assistant. It's a demo that we built that showcases this interaction of machine learning, combinatorial optimization, and explanations. So you can download it on the Google Play Store, and then you take a picture. For example, if you're solving a Sudoku, you just take a picture of it. There will be neural networks that analyze each of the cells. These neural networks will make mistakes, but then our solver can correct it because of that line of research that we do, which I'm not talking about today. But then what we also added in the app is if a user takes a picture, it probably means that they're stuck, right? And so you can totally ruin the game by showing them the solution. You know, that, okay, you know, bye. But instead, what we want to do is we want to help the user. So what we're going to do is we're going to compute the easiest next step that the user can take next. And so it's actually an explanation of one of the empty cells of how you can derive that information. So for that, we're telling the user you only need to look at the yellow values, and you only need the constraints that are highlighted here. I don't know if you can see it, but that means that there is a certain value in the green box that needs to be there. And if you look at this and you know Sudoku, you will know what that value is. Okay, so we are running this. It's on the server, but it's in the app. We compute it live. You just press the button and it computes this live. It's like about 1 second per run. So this works nicely. The library that I'm using in all of these examples, and which is also behind the app, is a CPMPy library. It's a constraint modeling library in Python. It's actually very much like Minizinc, except that it's in Python and NumPy based, which makes it easier to interact with machine learning algorithms. And the second key property is that it offers direct and incremental access to the solvers, because we interface to the Python interfaces of the solvers. So we don't use file formats, and that means that you can do incremental solving, which will be a key thing to make these methods work efficiently. So we have a ton of solvers. Choco is almost ready. There's still some bugs. Yes?
Can I ask a question?
Yes?
For example, what if the solver is not able to propagate or remove the value? That doesn't matter?
Remind me later. Yeah, because it's not about propagation level explanation. It's a set of constraints, but I want to explain some more stuff before I get back to that. Yeah. Voila, so that's the library. It's also what's running behind this presentation. Okay, so just to show you more that this is not just about toy problems, it's not just about SAT problems. What we will use, and one of my PhD students, Inyas, has prepared a lot of many of the examples that we will use here on scheduling benchmark. So this is from a nurse rostering data. So it's from the scheduling benchmarks websites. So in nurse rostering, you have different nurses. These names are fake, but you know, it makes it look more real. There are requirements on how many nurses you need on the different days, and also on when they can work, when they cannot work, how many weekends they can work, how many consecutive shifts they can work, and they have preferences about when they want to work or when they do not want to work. Okay, so it's pretty real life from that data, and that's what we will use as a running example here. Okay, so the outline of my talk. We'll start with deductive explanations. This is the biggest part of the talk. And then we will go to, sorry, let me just control the zoom a bit. And then we'll also talk a bit about these counterfactual explanations. Okay, so let's get started. So deductive explanations for unsat problems. If we take all of the preferences of these nurses on what days they do or do not want to work, and we make a decision problem out of this, and so with all of the preferences as hard constraints, then there is no solution. Okay, so let's start with this. There's no solution found. And actually this model has 168 constraints. Okay, so these are like the temporal shift constraints, but there's also the preferences as constraints at the bottom. And a day off or requests not to work. That's at the bottom. Requests not to work. Not to work as for this work. Okay, so 168 constraints, and your problem is unsatisfiable. So if you want to know why it's unsatisfiable, good luck, right? So if we look at why this problem is unsatisfiable, all we know at this point is that all of the constraints together make the problem unsatisfiable. Okay, but do all of these constraints actually contribute to it? And if you think back about the graph example, and the answer will be no. So a more reasonable explanation to show is, for example, a minimal unsatisfiable subset. So that's a set of constraints that are still unsatisfiable together, but you cannot remove any of the individual elements. If you would remove any individual one, it would now be satisfiable. And so you really need those, and none of them are redundant. You need all of them. And if you would show this, of course, there would be a lot less constraints for the user or for the planner to look at. All right. So how can we do this? This concept of minimal unsatisfiable subset, it's a very well-known concept. Jean-Marc Silva has worked a lot on that. And one of the simplest algorithmic algorithms for this is a deletion-based algorithm. Okay, so if I implement this in Python, or CPMPy, it looks like this. We get the constraints, and then what we do is we will try to remove each one in turn. So you remove one of them, then you have 167, and then you check, does it now become satisfiable? If I remove this, does it become satisfiable? If it becomes satisfiable, then if you remove it, it's no longer unsatisfiable. So that means that that specific constraint is one of the causes of the unsatisfiability. Okay, so if you remove it and it's now set, you need it. So you keep it in. If you remove it and the problem is still unsatisfiable, then it was redundant, right? I can just show 167 constraints. That one didn't contribute. Okay, and then you just try that for all of them, and that's it. Okay, so let's do this. What's naive is not defined. I didn't run the... Yeah, so if you do this kind of procedure, you actually have to debug your presentation as well. But in this case, it's not a bug. I just didn't run the cell. And so it's running the code that you saw on the previous slide. And well, it takes some time because you're going to solve 168 models. And each time you're reconstructing the model from scratch. Okay, so it's first 167, 166, 165. And so each time from scratch, the solver has to solve this, which requires patience and which would be bad news. But there's good news coming after this. So when this is finished, hopefully soon, I will show you the algorithms that we actually use that use assumption-based solving. You have a question?
So most of them are minimal and not minimum, right?
Minimal, yes. So they're subset minimal,
but for
not
the
minimum.
user, might it be more useful to get the minimum explanation?
I absolutely agree that you want the cardinality minimal and you want the smallest one, and we will get to those algorithms. Yes. Yes. Okay, so when I ran this before, it was 50 seconds. I think we're at more than 50 seconds now. Let's see. There, 74. Okay, so it's having a bad day today. Okay, so 74 seconds if you would do it naively. Now this assumption-based solving, which I will explain. Let's run it. 4 seconds. Okay, that's a gigantic difference, right? So this you could never run in a real application. This starting to become possible. Okay, so let's have a look at what the difference is between those two algorithms. Well, okay, let me just highlight the key things that we do differently. This part looks very similar, right? But what we're doing is we're actually adding stuff to the model. We're creating one indicator variable per constraint, And then, so this is a vectorized operation. We're saying for each indicator variable, there's an implication. If this Boolean variable is true, then that constraint must be true. Okay, so we create like an implied model with these implication variables, indicator variables. And then we're going to create our solver, and we're going to say to the solver, find me a solution and assume that all of these Boolean variables, these newly created, are true. So that sounds stupid, right? You create a lot of extra variables, and then you say to the solver, well, I'll just assume they're true. Okay? But it will not be, and I will tell you why on the next slide. So something that this enables solvers that support assumption variables is that you can get an unsatisfiable core from the solver. So the solver itself, if it reaches unsatisfiability, it will itself be able to tell you this set of assumption variables caused the conflict. It's not going to be minimal, and so there will be too many in this. There's no guarantee, but it will already usually be a lot smaller than what you started with. Okay, so that's the first important part, to be able to extract the separate core. And then the second one is that if you call your solver again, you're going to give it different subsets of these assumption variables. And if the solver is smart about it, then it will actually be able to reuse information from its previous solve calls. So it becomes incremental, and each of these solves will be much easier. And that is why the time is so high. Okay, so I want to give you just a bit of insight of what is going on in these assumption-based solvers. And for that, I need to explain the basics of set solving, of conflict-driven clause learning solving. I'll keep it fairly high level, but so a set solver, it only accepts a set of clauses as constraints as input. Just like a ACP solver, it will make some decisions. Those are the boxes in blue. Just like a ACP solver, it will do propagation. It can only do one type of propagation, or mostly that's unit propagation. Those are the black boxes. And then it might detect a conflict. It might see, in this branch of my search tree, so that's one branch of the search tree, I actually get a conflict, okay? So that's the conflict detection part of a CDCL. The next part is the clause learning. So if it encounters a conflict, what it will do is it will analyze why this conflict happened. So for example, if we take the before last propagation that happened, it has this clause X or not Y or Z, and that one forced Z to be equal to 1. But we have another clause, another constraint here in the data, here, that says not Y or not Z. And so because of the current assignment in this branch, it actually wants Z to be 0, and that's why there's a conflict. Now you can apply resolution on these two clauses. That means that you take them together and you remove Z because it now contains Z and not Z. And then you get a new clause that says X or not Y. Okay, so by doing resolution, you learn new clauses. And you keep doing this up to a well-defined stopping criterion that I don't have time to explain. Okay, so you keep doing this, and that's then a clause that you learned and that the solver will add to its set of constraints, to its set of learned constraints. Okay, now we do the assumption variable trick. Okay, so for each of our constraints, we added a Boolean variable that implies that constraint. And so in clausal form, that means that you can just write not A1 or the original clause. Okay, so everything remains clausal. Very nice. In each, actually, and then importantly, so the solver will assume each one to be true. It's not going to pre-process all of these away, but it's going to fake in its decision, in its search tree, as if it has set all of these to 1. Okay. And then everything else remains the same because it assumes all of these are 1. So exactly the same clauses and the same decisions will be met. Again, there will be a failure, but now in the resolution, it will also add the assumption variables. Okay, because they're in the clauses, they remain there, they're not pre-processed away. And so the clauses that you learn include the assumption variables. The real point I'm building up to, final slide about this. This now allows those two things that we need. First of all, if it has proved unsatisfiability, so in the very last branch of its search tree, if it's doing the clause learning there, it will end up with a clause that only contains assumption variables, right? So it will end up at decision level 0, and it ends up with only a set of assumption variables, and that is an unset core. Right, so in the very last branch, it just needs to answer that. And this will be much smaller than the original set of problems in almost all cases. And secondly, also importantly, this repeated solving, because each of the learned clauses include the assumption variables, the solver can keep them in its learned clause database. If you now give it a different set of assumption variables, for example, I only give it those, then this learned clause, well, that's not a learned clause, but just this is a learned clause, which is unfortunately turned off. Also includes 84. Okay, so this is my example. And so if I would only give it these ones, actually that learned clause would still activate. And that's why it can be incremental. Okay, so that's to come back to this. And that's what allowed that huge runtime difference. Okay. Now, I only talked about SAT solvers, and actually a lot of the work on explainability has been in the SAT domain so far, but things are changing. So this is not just for SAT solving. So nowadays, in constraint programming, we have lazy clause generation solvers and OR tools. OR tool CP-SAT is a lazy clause generation solver, and it supports, that means that it translates to SAT dynamically, lazily. So it supports assumption variables, and it supports unset core extraction. The Python API is not incremental, but okay, this is already a lot. There's other solvers like pseudo-Boolean solvers are sometimes also based on top of SAT solving, or in the case of the solver that's in CPMI exact, it's actually a conflict-driven cutting plane learning solver, but it also supports learning and assumption variables. In submodular theory, many SMT solvers are built on top of CDCL algorithms like Z3, so they also support that, and also within MaxSat. Okay, so it's not just for SAT research. All right, so this minimal unsatisfiable subset is a deductive explanation. Okay, that set of constraints, they are minimal and they minimally entail the failure. Okay, so let's apply the algorithm on our 168 constraints. I think we already did so, but it gives you a length 11 mus. Okay, so from 168 to 11 constraints. Now you only have to investigate those 11 constraints. We have some nice visualizations. Okay, it's less work, but still quite a lot. And you already asked, what about the smallest one? So actually, it's true. There's not just one minimal unsatisfiable subset. There's going to be many, well known in the community. So there are some very nice algorithms. In this case, the Marco algorithm. I'm not going to actually show the algorithm, but I'm going to run it here. Okay, so this is with an incremental solver. This exact solving solver. So every M here is a mus. Okay, I've put a timeout of 15 seconds. So this enumeration algorithm found 105 different musses in 15 seconds. So in a fraction of what it needed, if you do research, it can find 105 musses. So why would you settle for just one? Why? Yeah. So actually, my student he ran this over the weekend, over a weekend, also read some time. So this little problem, just 168 constraints, has over 100,000 minimal unsatisfiable subsets. Okay, and this is the size of these musses, and that's how many there are of that size. So there's even one of size 3, just 3, but there's like more than 5,000 of size 31, 32, 33. Okay, so if you just run your mus algorithm, and we got 11, we were still pretty lucky, but you might as well get this one or even this one. Okay, so then the question is, if we actually want to show these explanations to a user, can we actually influence what mus is found, which type of mus is found? So first algorithm that we're gonna see is the quick explain algorithm. Again, very well known and also very widely used outside of the CP community. Okay, so it was proposed within the CP community, So model-based diagnosis, even recommender systems in verification and support, they use this quick explain algorithm. It's a divide and conquer like algorithm, and it takes a lexicographic preference over the constraints. So it assumes that each of the constraints are ordered and that you want a mus that includes as many of the earlier ordered ones and as few of the later ordered ones. I'm not going to go over the algorithm because it's actually not super easy to understand from the code, but I worked out a little example. So this is my figurative eight different constraints. I want to have as many of the ones that are ranked here and as few of the ones that are ranked here. Okay, so quick explain, it will always halve the set of constraints and work recursively based on that. So initially it's going to take just the first half, the one that you really want, and it's going to ask, are these unsatisfiable? Okay, if the answer would be yes, you can throw away half of your constraints. That would be great. But the example is contrived and it's not so great. So it tells you sad, so okay, no, you know that you need at least one of those. All right. So it again successively halves the orange set, and it will ask, maybe I only know these ones. And say, no, bad luck. Okay, so then it successively halves this, and then it says, okay, is this unset? Yes, it's unset. Then there's a special case that you can find in the code. So you know that this one has to be in the mus. And then it continues. So it will only ask it about that half now, and the one that you skipped here, about that half. This is unset. So we can throw, with one call, we can throw both of them away. Okay. And then we will investigate this one. So we only check with that one, halving, and then it finds the solution. Okay. That's how it works. So if you want to understand it better, that would be it. Now, in this case, it's a bit of a contrived example. It actually needs more calls than the number of constraints.
What's the guarantee in terms of the
K log n.
No, I'm sorry. What's the guarantee in terms of the quality?
So the quality is a user preferred ordering over the constraints. So it will guarantee that it will only use these constraints if there exists no mus that needs that constraint. Right? So the mus that you get, this one says that there is no mus that without a 7 or an 8. So within your preference, you really need that least preferred one of you. And if you have that one, then the second least preferred one that you need is this one. You really can't do that. And so
and it is unique now because of this technical.
that's a good question. That's a good question. Yes, yes. Yeah. Okay. Yeah.
I would guess that before trying to get the information, you first run them all, get a value, and then you have to define. Would you like
First run them all?
I mean, you first run the model.
Run the model, yes.
Then you
Yes.
if you like, extract the number of values that are involved in the first solving case, that you can like initialize the weights of the constraints.
Yeah, but the goal here is that, for example, in the Sudoku case, these are application-oriented preferences. For example, I mean, you can do what you do, but it's not going to help the user. In the Sudoku case, we want to use as many of the previously assigned facts, the many of the values that are already filled in, and only then do we want to use constraints. Because sometimes you can add constraints in your explanation that rediscover a value, but you can just use the value, right? And so that's, for example, an end user application here. In case of the so what I do here, actually, it's also an algorithmic one. So in the first one, I say I want the largest constraints to have my preference, which is a city ordering, or I want the smallest constraints to be first. Because if you care about interpretability, then this one is a meaningful one. Let's try to have an explanation, and let's try to have as many small constraints in it, and the big ones, for example, cumulative, the composition, whatever, less. Okay. So if we do this, semi-ordering, we get a mus of size 18. And if we use this smallest constraints first one, we get a mus of size 3. Okay, here we're very lucky. It's the smallest one that you've seen in the previous incomplete enumeration. Okay, runtime doesn't matter much. Okay, so why is this algorithm so popular? So here I use exact, this incremental assumption-based solver, and I'm now going to use OR tools without the assumption variables, actually with, but it's not incremental, right? So OR tools is not incremental, and I'm gonna run this algorithm, which took 70 seconds when I did the deletion-based mus, okay? And here, it just needs 4 seconds. Okay, complete restarts. It doesn't do anything incremental, but because the quick explain algorithm is this halving algorithm, and because our mus is tiny, like 3 out of 168, it actually can throw away, in the first call, it throws away half of them, right? In the second call, it probably throws away half of them again. And so that's why this algorithm is so popular. You don't need incremental solvers, you can run it, and it will actually perform reasonably well. Okay, now, your question, okay? Can't we just find the smallest one? Let's say that we give each one, you can, or even a weighted one, and you can give each one a weight of 1. Can we actually find the very smallest one? Okay. And for that, I need 3 properties to explain to you. The first one is that if you call your solver on a subset of the constraints, and the solver says that this is a satisfiable subset, then you can actually grow the satisfiable subset into a maximum satisfiable subset. Okay, so if you have a satisfied, you can grow it, and you can do that very efficiently. The second key property is that if you take the complement of a maximum satisfiable subset, then you get what we call a minimum correction subset. And now there's a theorem, and that says that a minimum unsatisfiable subset is a hitting set of the minimum correction subsets. Okay, why am I showing this without any context? That's because to find the absolute smallest one, or even the weighted one, the optimal unsatisfiable subsets, we will use an implicit hitting set algorithm. And so what this implicit hitting set algorithm does is it will use this hitting set property, right? So it will dynamically compute MCSs because you don't need all of them, and then it will take a hitting set of those, and if this one is unsatisfiable and size minimal or weight optimal, then you found the one you want. Okay, so it will incrementally find this one well. Okay, so you have to initialize it. Your initial hitting set, your initial MCS, will just be the set of all constraints. That's valid because no constraints is satisfiable, so all constraints are unsatisfiable. Then it will call a set solver, and then it will compute a hitting set. So this will just be one constraint out of your set, and it will ask the set solver, is this satisfiable? And so the smallest one here would be just one constraint. If the set solver says yes, then it means that you didn't find an unsatisfiable subset. Okay, so you're not done. It says yes, so it means that it's satisfiable. So it means that we can grow it. So we'll grow it, and we'll take the complement, and we will add it to the set of correction sets that we need to hit. Okay, so one more that we need to hit. We again ask for the optimal hitting set, so the smallest one, and then we'll call the solver. If it's set, too bad, that's okay, we grow it, correction it up. And then as soon as you found that a subset that is unsatisfiable, you know that this one is optimal, so it's for example a cardinality minimal, and it's unsatisfiable, so it is an optimal unsatisfiable subset. There's some nice theory that support this. Okay, now if you want to do this efficiently, and this is what we use in the app, you again need 3 components. First of all, your set solver should be incremental. And so here we again use an assumption-based solver because we're going to call it many times. Okay. Second of all, your hitting set solver should also be incremental, meaning that if you change the coefficients, no, we don't change the coefficients. No, I'm talking about here, if you add a constraint to it, an additional set that it needs to hit, you just add a constraint to it, it should be able to find the hitting set efficiently. Okay. And so here we use, for example, mixed integer linear programming solvers. They're very good hitting set solvers. and a solver like Ruby, which is in CPMPy, is incremental. And then the third thing, that's an algorithmic trick. This is just about interfacing. The algorithmic one is that instead of adding just one MCS, if you can cheaply add multiple ones, for example, complementary ones, then that's actually going to save you iterations. So that's probably a good thing to do. And so if you do that, then we can now actually compute. I don't have the time, but it's about say 3-4 seconds. And so we can compute the optimal one. And now we have proven that indeed 3 constraints is the very smallest set of constraints that is needed to explain the failure. And these are the constraints. We can visualize them. So that's a lot less work than before, right? And so these ones cannot be taken, and then there's only 6 remaining, so you have a conflict. That's if you stare at a bit, you will see that that's the cause. Okay, good. This was the biggest part of the talk, or at least of the different blocks. All right. So we've now shown you how you can use this efficient and preferred unsatisfiable subset algorithms to explain unsatisfiability, a deductive explanation. But what if your problem is satisfiable? Is there also something you can do? Yes, very much. The question that we're asking in that case is, how can we explain the satisfiability of a problem in a human understandable way? So when you use a solver, there's 2 things going on. There's propagation and there's search. Search, there's nothing to explain. Okay, that's just an arbitrary choice of the solver. But propagation, there is something to explain. Right? So propagation is a consequence, something that is a consequence of the constraints. So if we want to explain a satisfiable problem, we can't explain anything about the search part, but we can explain the maximal consequence of the current node in the search tree, of your current initial assignment. Now, in case of Sudoku, the maximal consequence, so what is it that you can derive from all of the grains together? That's actually the full solution, because it's a unique solution. So if a problem has a unique solution, the maximal consequence is that solution. Yeah, so a logical consequence is a variable assignment that is entailed by the constraints, multiple constraints, so not just one propagator, to get back to your one. So multiple constraints and the current partial assignment. The maximal consequence is precision maximal partial assignment. So that means that it's the intersection of all possible solutions. Okay, so we can compute the propagation consistent consequence by just running until fixed point. And then we have all of the things that individual propagators can derive. But we can actually compute the maximal consequence if we take the intersection of all of the solutions. There are some nice algorithms that do this, which literally take one solution, intersection, ask for a different one, intersection. So you can compute that.
And so it's more efficient than
the demo? But yes. Yeah, because you only need, if you find one solution, you say, okay, find me another solution that does not contain at least one of these. And then you find another solution, you take the intersection, and you see, is there another one? Is there another one? I should have included it. I'm going a bit fast. I don't understand. There are algorithms, yeah. Elegant ones. Okay, so in case of Sudoku, the intersection of all possible solutions, if you have only one solution, is of course that unique solution. Okay, so what we then do, and that's also what we do in the app, is we say, okay, for each of the empty cells, can you now, rambling, sorry. Yeah, so the maximum consequence is all of these greenly highlighted ones, so the empty cells in your original image. And so can we now explain that? Well, what we did in that paper is we do a stepwise explanation. That means that we initially only want to explain one variable assignment in that maximal consequence. We're not going to explain all of them, just one of them. And if we have that one, we're going to explain another one, the next one, and then the next one, and then the next one, and then the next one. And in that way, we can explain each of the assignments, individual variable assignments in the maximal consequence. And in case of Sudoku, you end up with the complete solution. Okay. And then of course, each of these, we want them to be minimal, or actually size minimal in this case, and so forth. Okay. Yes, so let's say that we want to explain this little cell here, this green 5. So what would be one individual explanation step? It's something that explains what you need to entail. So what is it exactly that entails that partial assignment? That entails that this is a 5. Okay, and if we want it to be as simple as possible, it means that we want as few of these facts at the previously derived cells, and we also want as few of the constraints as we can. Okay, so how do we do that? Actually, we know that n, for example, that cell equals 5, that's a consequence. So if we add the negation, namely that cell cannot be 5, if we add that, our problem, our entire problem is now unsatisfiable. And that's great. Okay, we've never been so happy that our problem is unsatisfiable, because now we can use quick explain, we can compute minimal, or in our case, we can compute the size minimum, cardinality minimal explanations. Okay, so that's actually where our research into this optimal satisfied system comes from. Okay, and we can do that for each one of those, and so forth. Now to do it efficiently for the entire maximal consequence, there is one additional algorithmic improvement that we did, is that we're not going to do it for each element of the consequence individually. We're actually going to formulate the problem over all at once, but we're going to add a meta constraint. We're going to say, find me a subset of constraints that contains one of those negated consequences. Okay, and we can do that just by adding a constraint to our hitting set solver, and this is a MIP solver, so it's very happy to get additional constraints. Okay, and then we can find one step with just one run efficiently. Not discussed in more detail because I want to move on. But so unsat, we saw sat, where we can do stepwise explanations, and to explain each step, we actually turn it into an unsat and use these algorithms, right? Now let's have a look at explaining optimality. And so that's the example that I started with. Why can't we use 3 colors? Okay, so a deductive explanation of an optimization problem is, can we explain why a certain solution is optimal? So why there does not exist a better solution, okay? Now, nowadays in CP and SAT, we have solvers that cannot just return unsatisfiability or optimality, but that can also return a proof of optimality. So you might wonder, can't we use that proof of optimality? And there's a number of reasons why this is not the most obvious route. I'm not saying it's impossible, but it's not the most obvious route. So indeed, many solvers support proof logging, including CP solvers like the Glasgow constraint solver, one of the newest solvers out there. These proofs, when a solver actually makes them, the solver wants to do it very efficiently. So these proofs are really built for computer verification. They don't care about explaining something to an end user. And it actually can become, these proof logs can become very large in size, up to gigabytes. So it's really not about communicating to users. And secondly, even if you would post-process the proofs, they also contain the learned clauses in these set solvers, okay? Or anything else that is available to the solver, which is not meaningful to a user. So this is not the route that we're taking. Instead, we're going to build again on the algorithms we saw before. And so if C is our set of constraints, and we had the graph example, so that's all of our not equal constraints. Fx is our objective function, the mathematical formulation, namely the number of colors. And then O is the optimal value, namely 4. Then, why is it 4? Why was it 4? Because actually it's the constraints, when you minimize the objective function subject to the constraints, it's actually the constraints that determine that it is 4, right? So it's actually a consequence of the constraints. And so if we add to our set of constraints an additional constraint that says that our objective function has to be smaller than 4, then the answer will be no. It will be unsatisfiable, and again, we're very happy. Right? We have an unsatisfiable problem. That means that we can again reuse all of the algorithms we looked at before: minimal, optimal, quick explain, everything that you want, and this will explain why it needs to be 4. So in the case of the graph, it was reasonable in size. 4, it contained 6 constraints out of the 10, I think. So it's, in case of explaining unsatisfiable, it's typically very, very big. Okay, if you would do this on a scheduling problem, you typically have all of the constraints involved. Okay, so that's not very clear to the user. So again, let's use some of the concepts that we know. Can we actually provide a stepwise explanation of unsatisfiability? So can we rebuild individual reasons, individual consequences that lead up to the failure? Yes.
For example, for scheduling problems, would you get smaller explanations if you use the decomposition rather than like the global constraints in this case, or would that still include usually just all of them?
So we put the set, what for us is one constraint is at the CP level. So it would be the cumulative constraint. And how the solver uses that doesn't matter for the user. So any answer will contain the entire cumulative constraint. Unless we do nested, that's, yeah. So, but it's at the level of entire constraint, and you define them. So it will be the entire cumulative. Okay, so can we provide stepwise explanations? The answer is yes. So this was a paper at CP last year, yes, for 2024. So there's a number of challenges if you want to do this, more than if you want to do stepwise explanations of satisfiability. Namely, in this case, we want to find these individual steps up to a conflict. But how can we do this with as few as possible steps and also as small as possible steps? So this one, you can now imagine the kind of techniques, this one less. Another problem is redundancy, not just at the level of an individual stepwise explanation, but also at the level of the entire sequence. So we actually have to post-process the sequence to remove any consequence that we didn't use to reach the final conflict. And then also how to make this algorithm fast and incremental. It's also a challenge. So I'm not gonna actually explain how we do that, but I am gonna show you what it looks like. So in this case, we take our 11 size bus, and I'm taking a complex one. So why does this lead to a failure? If you look at this, it's not very clear, but we can decompose this bus. So we're not going to go to failure, but just we're going to explain, we're going to zoom in and explain that single must, which is exactly the same technique. So we can find a sequence of 11 steps that actually explains this conflict step by step. Let's do this. Okay, first one. Catherine has a day off on the first Saturday. Okay, so she's free on that day. Good. Second one, Richard has a day off on the first Saturday. Okay, another person that's free. And then Robert, more Robert. Oh, I didn't run. Yes, more Robert, more Robert, more Robert. So these are all of the days that he requests to work. So he requested 5 days. And then there's a constraint that says that a nurse can only work 5 consecutive days, and then they need to have a day off. And that's literally what it says, right? So we added a textual description to each of the constraints up front. So that one needs to be, that nurse is free as well. And then it must be covered by 5 out of the 8 nurses, and 3 are already off. So it means that all the other ones need to work that day, including Kevin. Okay, now Kevin should work at most 1 weekend. So if he works this weekend, he doesn't work that weekend. It's also a constraint. But Kevin requested not to work on this Sunday. On this Sunday, and so that's our conflict. So that's then I started at offset 0. So that's our final one. And so the thing that we derived from the previous one is actually in conflict with that constraint, And that's why this set of 11 constraints are unsatisfied. Okay, so I hope you can imagine that by doing this stepwise decomposition, 11 constraints seem total chaos before, but with this, you can actually understand reason. And this is not at all what the solver did, right? The solver learned clauses, took some derived additional things, stuff, but this is exactly the steps that can minimally explain what is going on. So it's built to have small steps, and each step should also, small number of steps, and each steps to be small. All right, good. That was part one. Till what time do I have? That was the biggest part, so that's fine. Max half an hour. So the original timing was 15 minutes, I guess, then? Did you say max half an hour? Yes. Okay. All right. So this one is shorter. No worries. Let's do this. Okay, together. All right. Small recap. We had deductive explanations. What causes X? What set of constraints causes that? And now we're going to look at counterfactual explanations. What if I change something, right? And what kind of solution? So in these counterfactual explanations, you both need to relax your constraints. And the reason you're going to relax them is because you care about the solution. Okay? This answer doesn't say anything about the solution. This answer tells you this is what you have to change, and that's what you then get. And then the user can decide, and the hotel owner can decide, okay, am I going to call one of them and ask if they maybe can come a bit later or whatever, or maybe I want this person and this, or it's like a maintenance work, and so I'm just gonna postpone the maintenance a bit, and then we'll do this. All right, so a must explains one conflict, and then maximum satisfiable subset is a relaxation. So if we want to find a counterfactual explanation for an unsatisfiable problem, then we can compute a maximum satisfiable subset. Okay, so this here would be satisfiable, and then it means that we have to drop these constraints, and then we can compute a solution. Okay, so how are we going to algorithmically do this? Well, in this case, we can do even better. Okay, in the slide before, I showed you minimal, halving, and only then weight optimal. But in case of finding satisfiable subsets, we can actually find a maximum satisfiable subset. So the largest one, not just the subset large one, but the largest one, because that's where we have entire communities already working on, right? The MaxSat community, it's all about finding the maximum satisfiable subset. And same with optimization solvers in CSP, it's all about that. So we can again do the indicator variable trick. We add an indicator variable to each constraint, and then we maximize the size and the number of those indicator variables, and we get this. Okay, so if we do this on our nurse rostering problem, then the size maximal one is contains 164 constraints. So that means that we have to drop these just 4 constraints. If we drop just these constraints, then we get a solution. Okay, let's look at that. Thought I was going to show that solution. No, okay, we'll look at that in a minute. Ah, yeah, here, okay. So if we look at that solution, then what it did is it removed 2 preferences of individual nurses, but it also removed the entire requirement on this Saturday and the entire requirement on this Sunday. Okay, that's crazy. So it says, oh yeah, no problem. Just don't have anybody working on Sunday. Perfect. Okay. So from an algorithmic point of view, computing these MCSs, that's an interesting challenge. But if you take it now at CP level and you look at what it's actually computing, if you just delete constraints, you get totally unacceptable things. Okay. So how can we do better? Then we go into corrective actions, this word here. So deleting a constraint is actually a corrective action. A preference of a nurse that is not satisfied, it's something that you can do. It's a Boolean constraint. And if you say no, then that request is denied. But in case of this capacity constraint, the number of nurses required in that shift, there's actually an amount of violation. Okay? 0 is a lot worse than you ask 5 and you get 0. That's pretty extreme. So what you can do is you can introduce a slack variable for each numerical comparison, and that slack will indicate, so it's just another integer variable, I will show you that. It indicates how much the violation is. And now your optimization problem will be over the Boolean indicators of the constraints you don't mind dropping completely, and over the slack values of those where you want fine-grained control. So it's still standard optimization problem, still standard CP modeling, you just have more fine-grained control. And this recent paper from the Monash group also goes nicely into an application that needs that kind of explanations. Okay, so here's an example of how you would code that. Our slack variables are always positive variables. So in this case, we're going to have a slack variable if you put too many nurses than what was requested, and also a slack variable if you put fewer than what was requested. Okay. The way that you model this, you will count the number of nurses that are used. So you can use a global constraint here very nicely, show that you do need your CP solver in its full strength. And then you're going to add a constraint that says, okay, the count value here has to be equal to the requirement minus slack if you're going to do too few, plus slack if you're going to do too many. Okay, so these slack variables will absorb the number that you have more or less than the requirement. Okay, so it's just some modeling. Okay, I'm not showing how to do it for each of those, but we have here the slack model, and I'm defining an objective function, so I'm adding my preferences. I'm saying, first of all, penalize the worst violation the most. Okay, so that's the max of how few you have. Then penalize the number of violations in terms of slack variables that you do, under violations, and then also have a small penalty for adding too many nurses to compensate, because they also have a minimal number of shifts they need to work because they want to feed their family. So, you know, there's a contract. Okay, so that's how you can then play with user level preferences over these violations. That's not the goal. That's still not the goal. Okay, so let's visualize the solution. So now we get a solution. Saturday, our first Saturday and Sunday of week 1, they're still problematic, but the best we can do is that they each have 3 nurses less. Okay, so there's no longer nobody on the board, and there's at least 2 on those 2 days. And then there's a few too many here now, but that's less important. And there's also on this Saturday 1 person less. Okay. You might hire, a planner might hire a temporary staff to cover this weekend, for example. Okay, that's the user level way that you can use that. Okay, so I hope you agree that this is a more desirable correction to the original problem. Okay, and it was just modeling. ACP is great at modeling and so on. Okay. So that's how we can use these counterfactual explanations and changes to the model and new solutions in case your problem is unset. What if your problem is set, but you don't like it, right? So it's satisfiable, you got a solution, and the user asks, what if, why? What if something else? What if Mark would work on that day while he's currently not working instead of your current solution? So this why here is an important concept, and it's called, or yeah, in explainable AI, it's called a foil. And this foil, it's a bit of a silly term, but it's a partial, in our case, it's a partial assignment or a constraint that is counterfactual. So it's different from the solution that you got, from the facts that you have. Okay, so it has to be different. You're not going to ask, Mark is working on Saturday. Why doesn't Mark work on Saturday? Well, he's working on Saturday. Anyway, so a foil is something that is not in the current solution. So then we need to check our set of constraints plus this foil, this requirement that the user is interested in. And then you have 2 cases. Either that is also a satisfying solution, and then fine. Okay, then you just show the solution and you say, okay, here's what you wanted. It is possible after all. So in many cases, they don't like the solution, and what they do like is actually also possible. It's just not what the solver computed. Okay, so just with some modeling, we can do that. If the answer is unsatisfiable, that's where it becomes more interesting. So then the question is, can we now show either a deductive explanation or a counterfactual explanation of what needs to happen? So a deductive explanation would explain why it's impossible, at a causal explanation, and a counterfactual explanation would explain what needs to change here so that y is true after all. Okay, so in this case, you just go to any of the previous techniques that we discussed. Small example. We have a nurse, William, and William is currently scheduled to work on the first Saturday. Let's hope that's true. William, yes, first Saturday. Okay, so he's one of the heroes that is staffing on that difficult day. But there's a problem. What if he doesn't want to work? No, I don't want. He probably has a good reason. So yeah, hopefully. And so we add this constraint that says, okay, find me a solution on which William doesn't work on that Saturday. And then actually we in this case again compute the corrective solution. So we compute the counterfactual explanation. And we see that there is actually another solution. It has a higher penalty. So you're going to violate more constraints. If you're going to allow William not to work here, you're going to violate one more constraint, but it is possible. And then it would look like this. You would still have 2 nurses on those days, but now you have 1 less nurse on this day and 1 too many here. It's very less important. Okay? So the impact is there. And then again, the planner can say acceptable, not acceptable, and so forth and so forth. Okay. All right. And then final one, can we now also do counterfactual explanations in case the solution, if we have an optimal solution. So the first one is a bit related again to what we saw. So if you want to do better than your current optimal solution, and you have a set of corrective actions that you can define, like in the graph coloring example, we do allow constraints to be deleted. Well, then you know that this is unset, and you can get either counterfactual explanations. Well, in this case, you're only interested in counterfactual, and then you can get a counterfactual explanation. Okay, so that's what I did with the graph coloring example. So in case of the constraints, easy. And there's one final case I want to discuss and I want to present to you. And that is, what if we want to define corrective actions over the objective function? Okay. So if the objective function expresses preferences, then the question that you could ask is, what preferences need to change so that this FOIL now becomes the optimal solution? Okay. So the coefficients of the objective function, how should you change the preferences so that what the desired effect, what you know you want, is actually optimal according to that objective function? Okay, so here this y is a FOIL. It leads to a non-optimal solution. There's a very, very nice paper from Anton and Chris Beck exactly about this problem. Okay, so we're going to find an optimal solution. It uses a slightly different model. Don't care too much about it. So this is the solution that you get. Okay. In this solution, we have Robert. This time, Robert is unhappy. Okay, William is happy, but Robert is not. And these are the preferences that Robert gave to work on specific days. Okay, so he has a preference of 1 to not work on that day or to work on that day. And there's one specific one that he's unhappy with, namely his request to work shift D on Friday 1 is denied. So no, you can't work. He wants to work on that Friday, and he says, no, you can't. Okay. So the question is now, again, imagine Robert has some good reason. Maybe his daughter is having a surgery that day, or probably there's a good reason. So how can he minimally change his preferences over the other days? So he really wants to work that day, and he's willing to change his preferences so that he works that day. Okay, that's the question here. Can we compute what weights are needed to actually have that effect? And so algorithmically, I'm not going to go into the details, but it's really a beautiful inverse optimization algorithm. And so inverse optimization, what is the objective function to have that effect? And it uses, again, a MIP solver and a set solver, and you have incrementality and all of that. Okay, so I'm not going to show the actual algorithm. I'm just going to show that we have an explanation that goes nicely. And so it found a solution. It has the same kind of penalty, now not just taking slack variables, but also preference into account. And all Robert has to do is change one preference. This preference, namely to not work on shift D, has a preference value of 1. If he reduces that to 0, then actually he will be assigned to that Friday shift that he wants to. Okay, I'm not visualizing the solution. But so just one weight change is sufficient for him to get that shift that he wants, right? So I hope you can imagine that this is a good example of how it's still all CP technology, but you can actually empower your users to control the solutions. Even individual nurses can play with just their own preferences and see how it changes the solution, which is still guaranteed to optimize all the other constraints and objective value. Okay, view. So deductive explanations, counterfactual explanations, everything is covered, each one for both unsat and sat and optimization. The recurring challenges, one is that you always have to define the explanation. And defining explanation means that you both need to define the kind of question that the user asks and what the answer format will be. Okay? So I showed you some definitions, some ways that you can use this to explain that, but there's many, many more questions and answer formats that can be come up with, and for which we might have good algorithms or for which we might not have good algorithms yet. For computational efficiency, incremental solvers, especially closed learning solvers, are really key. Another recurring problem is which explanation do you show? And so even if you can compute the optimal one, maybe the smallest one is not what you want, maybe you want weights, but where do the weights come from? Can we actually learn these weights using machine learning? And we're playing a bit with that in the Sudoku case. So these are all very relevant questions. Also the type of user interaction. Our diagram so far was, it's a step, okay? So we have modeled the solve, and now we have one more iteration, but no way that it stops after one iteration, right? So how can we allow more iterations and interaction? Also visualization in this presentation. I often showed it in terms of visualization, so that's important. And there's more work on visualizing constraints, individual constraints, explanation, and support. And conversational, natural language, plenty of things to do. And then finally, what I didn't really talk about is evaluation. And so we're mostly, I showed you just computational evaluations, namely the runtime, or formal evaluations, namely is it subset minimal and support and support. But if we're talking about users, then it would make sense to also do user surveys, user studies, and so forth and so forth. So that last paper, that paper from the Monash group actually goes a bit into this. All right, so all of this work was part of that EU project that we have. We welcome visitors if you're interested, and I also have a postdoc position open, so don't hesitate to tell your colleagues. What I explained here is actually part of the wider explainable AI research field. It's a huge field. There's lots of work on explanations in machine learning, but there's also work on formal explanations in machine learning. So Alexei Ignatieff and colleagues, they use the similar implicit hitting set-based algorithms that I showed before with the ping pong. And so that's for formal explanation of models. In planning, very nice work in planning, minimal unsatisfiable goal sets, model reconciliation, all of these things. And also in KR, there's been a lot of work on justification that connects to this as well. Final slide. That's the conclusion. We saw deductive and contrastive explanations of each of those three kinds. The deductive ones, they can all be back related to musses or optimal unsatisfiable subsets. Okay, so that's very nice, and that shows again the key part of the algorithms. And also, if you want to do explainable constraint programming, you need some kind of programmable tooling. In this case, we use the MPy, and I'm quite happy with that. There's many open challenges, many new problems. the thing that's less developed is these counterfactual techniques, the second category, as well as interactive methods, more than just a single interaction. And also, I wished we had more incremental CP solvers. So if you like CP solvers, think about that incrementality and what it enables. Thank you very much.